With 1.5 million miles of pipelines spread across the country, how is it that we are not seeing catastrophes every day? Are these pipelines simply over engineered, or is there a science to the way they are designed, inspected, and governed? My name is Daniel Towner, and I'm here with Michael Lisove and Michaela Antelak, and we're here to present to you a tiny taste of the world of pipeline design. If you follow us on this journey, we will start at the whiteboard where design principles are combined with a keen knowledge of failure modes to produce safe and economical pipelines. Next, we'll fly above, travel within, and arrive wherever pipeline inspection is needed to ensure continued safe operation. Lastly, we'll take you to the books, where we will finish off strong with the establishment of applicable codes and standards that govern the design, inspection, and maintenance of our 1.5 million miles of pipelines. Speaking of which, Michael, can you tell us how pipelines are designed?
When designing pipelines, there are many factors that must be considered in order to produce a safe, efficient, and long-lasting pipeline. Way more factors than I can cover in this short amount of time, so I'm going to try to hit the major ones. As you think about pipelines, you got to think about location, above ground, below ground, temperatures, and pressures. And one of the main things that you really need to consider when you're designing pipelines is the maximum allowable operating pressure. And that's what I have up on this slide. The reason it's very, very important is because it's a government enforced pressure. So the 49 Code of Federal Regulations 192.105 gives you that equation, and you got the factors such as specified minimum yield stress, the pipeline wall thickness, design factor, joint factor, temperature factor, which we'll cover in a second, and the diameter. So you basically get all of your numbers together and calculate that out, and you have to make sure that you meet the codes. The maximum allowable operating pressure is often less than 0.6 of the yield stress, and the reason that's really important is because it allows for hydrostatic testing in the pipelines to occur at high pressure so you don't actually reach the yield stress, so thereby avoiding the plastic deformation of the pipeline. And these are the factors that I was talking about in the previous slide, as well as the equation from the previous slide for the maximum allowable operating pressure. As you can see, there's 4 classes that they can go through, and it really depends on the number of buildings within 220 yards, or if the building has 4 or more stories, you get a class 4, or if it's offshore, you have a class 1. So the next factor in pipeline design that I wanted to talk about is the actual material selection. This comes down to a discussion of brittle versus ductile materials, basically. Pipeline which includes a small flaw or crack will not propagate as easily in a ductile material. The more ductile material, the larger process zone ahead of the crack, and it'll plastically deform and absorb the energy rather than propagating the crack initially. With ductile materials, the critical flaw sizes are much larger than with brittle materials, and it's much easier to detect and repair the cracks before they reach an unstable propagation. Ductile materials are also generally easier to manufacture, which reduces costs. The big thing here is you're looking at a selection of the materials based on fracture toughness and yield strength. You want to have a large value of that. Again, the ductile materials are preferred due to their ability to absorb energy. And I've got a nice, created an Ashby plot there. And if you haven't seen those before, you basically put in your parameters and it graphs out a material selection for you. On this one, I graphed out the yield strength versus fracture toughness. And for the best materials for the selection in this criteria are the ones at the top right. So basically it's the steels and the high strength alloys that will give you the best fracture toughness and yield strength. As I talked about initially, pipeline stress and fatigue really depend on the pressure and temperature and the possible expansion in the piping materials. The codes vary on the way they calculate the stresses, but there's an example of one of the ways the codes do it. The fatigue life is normally calculated based on a 40-year fatigue life, and it's dependent on the allowable stress ranges and pressure cycles. One of the big things is what the vicinity is of the piping towards the compressor station, which really, as we talked about in class, can create those cycles in the piping. Another important aspect of pipeline design is stress corrosion cracking. It's something that you always have to be aware of when you have the presence of a susceptible material, a sufficiently high tensile stress, and an aggressive ion. I wanted to focus more on how you prevent it. If you take away any of those 3 parts, you will prevent the stress corrosion cracking. So you can keep your stress intensities low, you can do shot peening, or you can do a pipeline coating combined with cathodic protection, which is basically an impressed current. On this slide, more stress corrosion cracking, just a table summary of the materials, the aggressive ions, the concentration, the stress levels, the temperature, and the failure mode, either intragranular or transgranular. And it kind of gives you an idea of the conditions that are required to have stress corrosion cracking that you have to design against. For the last slide on design, I wanted to bring up that there's numerous other methods that pipelines can crack and corrode. Two of these are pitting corrosion, which can occur in stainless steel. It's produced by chloride ions, which damage the passive oxide film, and weld cracking, where there's an improper welding technique and improper heat treatment, and then you get a crack that runs through the weld. Next, we're going to move on to inspection of pipelines.
Aerial inspection is often the first line of defense as it provides a cost-effective method of quickly surveying miles of pipeline without having to navigate through rough terrain and private property. Helicopters and drones are used to detect existing leaks and warn of foliage overgrowth and other threats to the pipeline. These airborne units utilize infrared laser pulses and reflection sensors to measure distances and the response change as the signal travels through leaked gas. GPS technology helps document the location, while inclinometers adjust for the airborne unit's pitch and roll angles. The use of photogrammetry allows the collected data to be post-processed and provide a visual topography for further analysis. The image you see here is an ALPA system from Lawson. It uses a light detection and ranging system known as LiDAR. Aerial inspection is often the first line of defense as it provides cost-effective methods of quickly surveying miles of pipelines without having to navigate through rough terrain and private property. Helicopters and drones are used to detect existing leaks and warn of foliage overgrowth and other threats to the pipeline. These airborne units utilize infrared laser pulses and reflection sensors to measure the distances and the response change as the signal travels through the leaked gas. GPS technology helps document the location, while inclinometers adjust for the airborne unit's pitch and roll angles. The use of photogrammetry allows the collected data to be post-processed and provide a visual topography for further analysis. The image you see here is an ALPA system from Lawson. It uses a light detection ranging system known as LiDAR. We all know pigs can't fly, but can they swim? Well, a pipeline pig is a device that runs inside the pipeline without halting operation. It is generally pushed along with the flow of the fluid. Some pigs are sent through for the purpose of cleaning and picking up debris, while others are equipped with sensors and loggers. The latter are called smart pigs and allow the surveying of vast distances of pipeline. The simplest smart pigs use calipers to measure geometric anomalies such as metal loss from corrosion. A more sophisticated metal loss pig uses magnetic flux leakage and can be useful for detecting large defects and wall thickness changes. Traditional ultrasonic tools offer the capability of detecting crack-like flaws, which has provided a major advancement in designing flaw-tolerant pipelines from a fracture mechanics perspective. Pigs such as Ultrascan can detect cracks that are at least 1 millimeter deep and 30 millimeters long. Because this is the resolution, if an Ultrascan passes through without detecting anything, one would have to assume that the initial crack length is indeed 1 by 30 millimeters. The Paris regime calculation would be employed to determine how long it would take before a crack of 1 by 30 would reach a critical size, and the next inspection would be scheduled before that time. As great as Ultrascan is, it does not work in gas pipelines because it requires a liquid medium by which to propagate the ultrasonic signal. The EMAT scan made by GE also uses ultrasonic technology, but with the use of an electromagnetic transducer, it is able to send and receive signals in both liquid and gas pipelines. The minimum flaw size it can detect is 2 millimeters deep, so not as precise as the Ultrascan, but it can be used in gas pipelines. Pigging has its challenges and is not always economically viable. Pigs can get stuck through tight bends or if a pipe wasn't properly cleaned. They also require a pig entry and exit stations. Not all pipelines, particularly older ones, are piggable. A friend of mine who is a chemical engineer who has been disgusted with the troubleshooting associated with smart pigs once told me, "No pig, no problem." Nevertheless, pigging can be very useful when it works, and I'm excited to see how this technology will advance, particularly in being able to detect smaller and smaller flaws. Just think about it. How much money could be saved if we could increase our resolution to, say, by a factor of 10? That could change the way we design pipelines, decrease our factor of ignorance, and increase the time intervals between costly inspections. Anybody know what that is?
That's a digital flux logger.
Not bad for a 4-year-old. After we do our best to survey via drones and pigs, sometimes we desire higher resolution or higher accuracy than is available through those technologies. In such cases, a crew would be sent out to location and sometimes have to excavate if the pipeline is buried. External handheld inspection devices are only practical for small areas and are generally only used where flaws are already suspected. Magnetic particle inspection, known as MPI, enhances the visual contrast between cracks and their surroundings. A solution containing tiny ferrous particles is applied over the area to be inspected. A strong electromagnet is passed by to temporarily magnetize the pipe, which causes ferrous particles to get stuck in the cracks, thereby making them easier to see under blacklights. MPI will not work on stainless steel, titanium, or Inconel. Liquid penetrant inspection, known as LPI, is similar to MPI as it relies on enhancing the visual contrast between the crack and its surroundings. A dye is sprayed over the inspection area, and the technician waits for the dye to penetrate into the cracks. LPI works both on mag and non-mag materials. Both MPI and LPI are very dependent on the skill of the technician interpreting the results and the resolution of the naked eye. The smallest flaw a person with excellent vision can detect is around 1/10 of a millimeter. Still, this is much better than the ultrasonic pig. Neither MPI nor LPI have good depth perception and are limited to cracks on clean surfaces. Olympus has developed an external pipe tester that uses eddy current array scanners known as ECA. These handheld devices don't require a clean surface and can detect subsurface cracks. It can detect cracks as small as 1 millimeter in length. It contains logging technology and displays the mapped flaw on a screen on a standard XY plot. Don't you think these inspection methods are pretty cool? I also love all the thought and calculations that go into pipeline design. But there's got to be some type of order to the way things are done, right? Michaela, can you explain what standards govern the way pipelines are designed and inspected?
There are numerous codes and standards relating to the design, fabrication, inspection, and maintenance of pipelines. Standards are a set of technical definitions and guidelines to ensure a common engineering and technical method for the design and manufacturing of many different types of hardware. When a government adopts a standard into law, or when a standard is incorporated into a contract, those standards become codes. Standards and codes are developed by committees of subject matter experts. In the following slides, several different American Society of Mechanical Engineers (ASME) and American Petroleum Institute (API) standards will be discussed for pipelines and piping design. This table shows the difference in codes and standards used in design and inspection of onshore and offshore pipelines and piping. ASME B31 series of codes govern the design, fabrication, and inspection of different types of industrial piping and pipelines. B31.1, B31.3, B31.4, B31.8, and B31.9 are several of the ASME B31 series of codes reviewed for a quick design and inspection comparison. 3 major ASME codes for piping design, we find that B31.3 is a very stringent code with a high margin of safety. B31.4 is less stringent than B31.3, and B31.8 is more stringent than B31.4, but less stringent than 31.3. Here is a table for a quick look comparison between several ASME B31 codes regarding the design allowable stress, factors of safety, and acceptance inspection method criteria. B31.3 is the more stringent code regarding allowable stress, being based on a factor of safety of 3 and with a 95 to 100% of all welds and joints being inspected for defects. Offshore piping facilities are governed by ASME B31.3. Onshore facilities are usually governed by either ASME B31.4 for oil or B31.8 for gas. However, many onshore facilities use the more stringent code ASME B31.3. Overall, as compared in the previous two slides, ASME B31.3 is considered the most conservative and will lead to a much more rigorous design. While ASME B31 codes govern the overall pipeline design, the API standards direct the types of pipes, the welding process and inspections, as well as the NDAT inspection requirements as referenced in the applicable ASME codes. API standard 5L governs the types of pipes allowable. API standard 6D governs the pipeline valve design. API standard 1104 governs the welding techniques and inspection criteria, and API RP 1111 governs the design of offshore hydrocarbon pipelines. While there are codes and standards that govern the design and maintenance of industrial pipelines, there are two government agencies that control all aspects of pipelines: the Federal Regulatory Commission, FERC, and the United States Department of Transportation Pipeline and Hazardous Materials Safety Administration, USDOT PHMSA. FERC regulates the transmission of natural gas, electricity, and oil on an interstate basis. The FERC also approves the sitting and abandonment of interstate lines. In large, this agency is involved in all aspects of getting a pipeline properly designed and operable. PHMSA protects the people and the environment and sets and enforces the standards and codes. The primary mission is to use the data, information, and technology to achieve their safety goals. In addition, they are the regulatory pipeline code enforcer during design and operation.
We hope that with this presentation you will gain a deeper appreciation of how engineers make the world a better place, providing safer and more cost-effective means of transporting the fluids that run our society. It's no wonder that despite the vast 1.5 million miles of pipelines, catastrophic failures are rare and becoming rarer. There's water, fuel, and chemicals that need to be transported to location, and now that we know how to do so safely, let the pipelines flow on.